Okay. Yeah, so welcome to week 9 optimization from fundamentals NPTEL course. We'll get started with the week 9 assignment questions, and with whatever time's left, we will solve a few more problems. So let's get started. The first question. So I hope you are able to see.
Yeah,
Yeah.
go on. No issues
Okay.
from my end.
Okay, so we are considering an optimization problem. It's a 2D variable, okay, and subject to some constraint. So our f of x, the objective, is a quadratic function x1 square plus x2 square plus x1 x2, and g of x is x1 square plus x2 square minus 1. So basically you're looking at a disk, unit radius disk, including the interior. Okay, and this constraint set, let's call it S. So there's a visible region.
Yeah, it's visible.
Yeah. So given this visible region and given this objective function, what we have is, let's say there is a point x star in S such that g of x equals to 0, that is on the boundary of the circle of this disk. Yeah, and at this point the tangent cone looks like this, all the directions t such that this gradient makes an obtuse angle with these directions. Okay, now claim is so this is the CQ, right? This is a constant qualification. So claim is that this constant qualification holds at x star equals to 1, 0. So just for concreteness, so this is my feasible set S. Okay, so yeah, what can we say about this? So first of all, at this point x star, where will the gradient for the constraint be pointed towards?
For this point, right?
Yeah.
So it should point towards the left, right?
I mean, okay, so basically orthogonal, right? Either here or here.
Yeah.
Depending on the function contours, right?
Yeah.
Okay. Anything else we can say apart from this? So this is just a constraint set, by the way. So I've not drawn the function. Function is actually this x1 square plus x2 square plus, so x1 plus half x2 whole square. So let's write it down. x1 plus x2 square minus x1 x2. Okay, so not right away obvious, right? What are the geometrically what are the things we can say?
Yeah, but it's not required either, right?
Yeah, here, yeah, that's true. So I just wanted to see if we can geometrically say something, but as of now, it seems like we can't say much more. So let's just go back to the information that we are given with. So okay. So is this true or false? Right. So CQ holds at X star that is given to us. So what does this mean? G of X star, is it equal to 0?
G of X star. Yes, right.
Yeah. So G of X, yeah. So what I'll do is go the other way around. I will see whether it satisfies the properties or not. So yeah, I mean, sorry, that's something that I have to prove anyway, so I have to check. So X star is 1 0. This implies G of X star equals to 1 minus 1 equals to 0. Okay. Anything else? Okay, so
So
yeah, just a second.
it should also be in this thing, right? The second condition.
Yeah, so yeah, the second condition is here, right? For the tangent cone to be
Tangent
this.
cone, yeah.
So right, so what is the tangent cone here? So what is the gradient here? So this is our constraint. x1 square plus x2 square minus 1. So the gradient is simply 2 times x, right?
2, yeah.
So this is 2x star and this is nothing but 2 1 comma 0, right? So the tangent cone is all d such that t transpose gradient gx star less than equal to 0. This is nothing but all d such that d1 is less than equal to 0. Okay. So what can we say then?
So this should lie on the left half plane, right?
Left, okay, but so okay,
the left
so
of the y-axis.
yeah, but so what do we really want to comment on at this point of time? I mean, this itself just shows, right, that we have just produced one such,
Yes.
right? We have produced one such tangent cone. So all that you are saying is there is a tangent cone such that, I mean, tangent cone can be expressed as this. We are precisely able to express it like this. So any d such that this d transpose gradient gx. So we can clearly find d all d such that d1 less than equal to 0. That's our tangent cone, right? So yes, the CQ holds here. At x star equals to 1 comma 0. Is it fine?
Yeah. this shouldn't be true, right?
Why?
Because the tangent cone, does this point lie in the tangent cone?
Which point?
X star.
No, we are finding the tangent cone at point x star.
Okay. Tangent cone at X star.
Yeah, so maybe what I'll do is I will explain it like this. So I'll just write an explanation. So what we really want to prove is okay. So what we will prove is, let's say dx star okay, so let d belong to dx star s, therefore d such that d transpose gradient gx star less than equal to 0. And what is this? This is 2 times 1 comma 0, right? So what we are getting is d1 less than equal to 0.
Yeah, so this is the specification of the tangent cone, right?
Yeah. So generally speaking, this is what I would need, right?
Because this is the general condition.
Yeah. So because we are looking at this specific x star point, the gradient happens to be this 2 times 1 comma 0. So we are getting this consequence that t belongs to d belongs to this set b such that e1 less than equal to 0, right? And similarly
and one small clarification I want. So this specification by this condition, that the transpose gradient of x star, this presupposes that we have a constant qualification in action, right?
No. So we should be able to express our tangent cone in this form. Then we can say the constant qualification works. The constant qualification is a sufficiency for you to be able to represent your tangent cone in a form such as this. So maybe let me write it separately here.
Got it. So it's the other way around.
Yeah. So CQ holds. This implies tangent cone at x star for a feasible set is intersection. Let's say there are m constraints. Okay. So we want a condition under which this happens.
True.
Yeah. So that's why we are saying constant qualification. So that's the reason why we introduced the idea of constant qualification. Okay. So just to complete this, similarly, what we will show is let the other way around. So t such that d1 less than equal to 0, dx star. So let d belong to this set. So therefore gradient gx transpose d equals to 2 1 0 d, right, which is d1, which is less than equal to 0, by star, right? Therefore gradient gx star transpose t is less than equal to 0. Is it fine?
Yeah, it's fine.
Okay, so that means that d belongs to dx star s.
Deep, just give me 2 minutes, as I told, right?
Yeah, sure.
Come back. I'll just come back after 2 minutes.
Hello, Soumyati. Can we resume? Hi, can we resume?
Yeah, you can resume.
Okay. Yeah, so just one how do I put it?
Yeah, are you speaking? I'm not audible. Yeah. Okay.
Hello, can you hear me?
Yeah, I'm here. I can hear you.
Okay.
Am I audible?
Yeah. Sorry, I just muted
Yeah.
myself by mistake. So,
Okay. No
yeah,
issue.
I just wanted to ask that the way we reasoned it, do you see any problem with the way we have argued?
No,
So,
I was actually the first. No. It's not right. I'm getting myself mixed up. Actually, that's not an issue with you. Uh,
yeah. So no. So the thing is, yeah. Let's just walk through the steps once more, okay? Because
yeah.
it is important. The definition is important here. So, the objective function, exact objective function, is not important right now. But we are focusing on the constraint, right? The constraint is basically this
Yeah.
disk of radius 1.
Yeah.
And so what we are given is, for this feasible reason, we want to look at what is the tangent code, okay, at some point x star.
Yeah.
So to recall our definition, constraint qualification holds at any point x star in the feasible region S if first of all the constraint has to be active. So I think I forgot to put an x star here. So if the constraint is active and the tangent cone can be described in this form, where you have all the directions such that they make an obtuse angle with the gradient of the constraint at that point, okay, x star.
Yeah.
So we want to know
Okay.
if this constraint qualification holds at x star equals to 1 comma 0, okay. So if this is
Okay.
our disk, right, this is our feasible region, and we are here at this point x star is 1 comma 0, right. So if we are if we are in this region, then we want to know if the constraint qualifications hold or not at this point. So what does it mean to say the constraint qualification holds, just to make sure we are on the same page?
Yeah. Okay. The constant quantification was it's intuitively it's just that we can write it as this thing, right? As constant is active, yeah.
So let's just go step by step. So
But
we want to know that there is a constraint qualification holding at this point, right, x star equals to 1 comma 0. So that means the first thing, what do you want to satisfy? Constraint should be active, okay.
yeah, constraint should be active,
So
right?
our constraint is active. Why? Because g of x star is 0.
Yeah.
Okay. So we'll
True.
just go step by step. So this is fine, and yeah, constraint is active. Okay. Then what is the next step? We should be able to represent our tangent cone for the point at this point
Right. Okay.
as something like this. Okay, sorry. So how do we do that? See, the mistake right now, it's the reasoning that we have done is circular. We are already assuming it to be of a form like this, and then we are saying it is of that form.
Right. Means the direction of implication is not clear now.
Yeah, I mean, we are assuming it, then proving it's true. We are already assuming it's true, so we shouldn't do that. We should be a bit
Right.
careful. Okay. So let's just remove all of this. Okay.
Yeah.
Okay, so again going back to the definition. So what do we have to prove now? We have to prove that the tangent cone looks like this, right? Okay, so what do we know right now? So next thing, so step 1 is done. Step 2 is, so we want to show that the tangent cone at this point x star 1 comma 0, that is nothing but all the directions such that t transpose gradient t star less than equal to 0. So again I'll come back to this initial point that I was trying to make. So if we are given this geometry of the set where it's a disk and we are looking at this point, so what all directions can we approach at this point x star from within the feasible region?
Yeah, this should be all to the this should all be to the left of that plane that is perpendicular at x star, right?
Yeah. So all such directions, right? So can we say something based on this? About can you directly say something about the tangent cone at this point?
Yeah, you can specify it just as in an analytical geometry, right? You can say that it should be you can specify that x is equal to one plane. All the points which are left of x is equal to one plane are my directions, right?
Okay, so how would I represent it as a set? So what we actually have,
Yeah, there may be some sound from it.
yeah, no issues, no
Do
problem.
not mind that.
Yeah, no problem. So what we actually have is what we want to look at the tangent cone at this point. So maybe if we zoom in a bit more. So if you are at this point, you can come from all possible directions, right?
Yeah.
Okay, so what can we say based on this?
Yeah, okay. So yeah, those should make an acute angle, right? With the normal. All those directions.
Okay, right. So what can we say in that case?
So if we specify the normal as
Yeah. So yeah, what do you mean by normal, by the way?
yeah, okay, the normal which is means acute angle. When I'm saying it, I mean that which is pointing inwards towards the side when the constant is satisfied.
Okay, yeah, sure. But see, you can
Yeah,
have a sequence that is coming in some all kinds of ways, right? You just want the resultant directions to be,
yeah, the limiting direction.
yeah. So that can be anything, right? It could be this, it could be this, it could be this, it could be this. Likewise, this, all possible things, right?
Yeah. So this is just if I specify that x less than equal to 1, that should be satisfied, right?
X equals to 1 is this plane. Okay.
X less than
it's
equal
this
to
line.
1.
Yeah.
Why we don't specify?
Yeah, it is this line. Yeah. Okay. So maybe let's backtrack let's see. So since we know the answer, we'll cheat a bit here, just for this one question, just to aid our thinking. So is this equal to, can we directly say this? So note that I am not saying this implies the definition of tangent cone. I mean the desired definition of tangent cone implies this description of my set. I'm not saying that. I'm saying, can I directly say this? Is it possible for me to say that?
For the tangent cone, right?
Yeah. In this particular case, is it possible for me to justify to begin with, based on the feasible reason that I'm given, the disk, the unit disk? Can I directly say that this?
No,
Yeah. Okay.
No, right.
Yeah,
we can't say this directly.
Okay.
Means how you are arriving at this statements from the definition.
No, so that's the thing. So we want to be able to represent it like this, but from the geometry we have something that we can say, which should look something like this, which also aligns with our own definition of tangent cone under constant qualification.
Okay. But we assume that we do not know anything about the formal definition, and just we try to intuit, right?
Yeah, let's say we don't know this thing that we want to prove, right? As in, let's say we don't know the form which we want, which is the d transpose gradient g of x is less than equal to 0. So we just have this geometry of the feasible set. So I mean, just to again recall, so for constant qualification to hold, what do we need? We want the constant to be active, and we want the tangent cone to be specified as per this d, such that it makes obtuse angle with gradient of g extra, right? That's our idea of tangent cone.
Yeah.
So how do we? But the thing is, like I said, I mean, we don't know this right now. This is our.
Yeah. 1 0. So just hold on. Yeah, I think we can write this like this, as we have written.
Okay.
It's possible.
Okay, but can you provide some explanation for why we can, from the geometry, write this?
Yeah, geometry. I see that because if you consider a vector to x star, that is just 1 0, right?
Yeah.
And if you take if you take the inner product of that with any general vector, and which makes an obtuse angle, with the 1 0 vector, that I believe should specify the tangent cone, right?
No. So there you are utilizing the fact that this definition is known, right?
No, I'm just telling you take a vector in the direction of 1 0, and you consider all directions that make an obtuse angle with the direction. So that gives the specified form, right? Which I just written.
Yeah, but why should that be the tangent cone? That's what I'm asking. So what you're saying is, this is my, just a second. So this is my x star, right? This is my vector.
Yeah.
And so you are saying anything that is obtuse.
Yeah.
Okay. Right, but any particular reason why you feel that should be the case?
Yeah, that's what means. This is. I don't know whether I am not. Means I think I cannot get my head around that for this moment. A little bit stuck around this.
I mean, you're on the right track. See, what we are really. So before what you were saying, we basically want to classify. I mean, we want to characterize this set of directions, right? So what are these points? W transpose x star less than equal to 0, right?
Yeah.
See, what I'm trying to say is, at this point, this is my normal. Yeah, that's
Yeah.
specified by X star. Okay, and
Yeah.
I'm just saying W transpose, which lies on this side. I mean, I'm taking the end product with W's lying on this side. So what do I
Yeah.
expect them to be? Less than equal to 0, right?
Yes.
So that is nothing but W1 times. So basically, that this is what W transpose. What is X star? 1 0 less than equal to 0, right?
Yeah.
This
That
implies.
gives the same form.
Okay. So yeah, I just
Yeah.
wanted to. Yeah, I deliberately went the wrong track. So to make sure that it's easy to end up using circular arguments and prove things. Okay.
Mm. Yeah.
So
Yeah.
okay. So let me just write it down carefully.
This was a little like splitting hairs.
So it is simply d1, sorry, d2 such that d1 less than equal to 0, because any vector on the left of the line x equals to 1 is a tangent direction, right?
Yeah.
This implies t transpose x is less than equal to 0, sorry, x star here it's okay, I'll just write x equals to 1, but here I'll write x star equals to 1. This implies t1 less than equal to 0. So I hope that, so what have we done? We have done both things. So and why is that the case? Because note that if I write another set, so let me call this set t2, such that gradient g of x star transpose d less than equal to 0, what will this be equal to? It will be precisely the same, right?
Same thing. Yeah.
Okay, so what do we have? T x star s is nothing but all d in R2 such that t1 such that t transpose gradient g of x star less than equal to 0. Okay,
Yeah.
I hope this is fine.
Yeah.
So we have done both. Yeah, yeah.
But we have been able to reason in this particularly simple way as the case is very simple. But in more complicated cases, we have to resort to the proper formula, right, for the tangent code on the definition.
Yeah. This just to give you a feel for, just to give you a simple example where you can actually see geometrically what it is and it aligning to our definition of constant qualification. That's all.
Yes. Just this is just to verify stuff. Yeah.
Yeah.
Get it. Yeah.
Just to give you a feel for it. Okay. So we have,
Yeah.
since 1 and 2 are satisfied, we say that CQ holds at x star equals to 1 comma 0. Okay, so yeah, that took much
Yeah.
longer than I expected, but it's okay. We'll keep on going to the next question. Okay, CQ1. Let me go back to notes. I forgot what is in by CQ1. Oh, okay, I see CQ1. Yeah, okay. So let me just mention what CQ1 means. Constant qualification, slightly different one. CQ1 holds at x star in some feasible region. So for constraints gi, so if there exists some direction such that for each active constraint at this point x star that is of our interest, we either have gradient of gi x star transpose c less than 0, or this is exactly 0 and the gi is affine.
So that means either it lies in the interior of the active constraint, or the active constraint is affine, right?
If you are in the interior, then the tangent cone will be the full space, right? Because you can approach.
Yeah, that's what it means. Yeah, so okay. Yeah.
Just stick to this for a minute. The second one is somewhat easier to see because I'm on a surface. So this one I hope is easier to see. I forgot to. I meant to write 0 here. Sorry. Sorry. You were saying something?
Yeah. Let's just stick with the definition.
Yeah. So
no, I was saying that it's either in the interior of the constraint.
So let's be a bit careful here. If you are in the interior of the constraint, then we can approach from any place, right?
Yeah.
So that means if I have gradient gi x star transpose d less than equal to 0, I can then also say gradient gi x star transpose minus d less than equal to 0, right? If I'm in the interior. Yeah, so that's why I'm saying. So it doesn't mean that we are in the interior. It's just saying, for example, here in this case, it just so happens that
I get it.
Yeah, it just so happens that I'm not allowed to go along this direction. I mean, not.
Yeah,
okay,
yeah.
Let me rephrase that. What I'm saying is this direction is not included.
Yeah.
Okay. Okay, so anyway, that was a definition of constraint qualification 1. We're just denoting it by CQ1. The question is minimize 3x1 cube plus 2x2 cube such that x1 plus 3x2 less than equal to 0. The claim is this constraint qualification, the new constraint qualification, it holds at the point x star equals to 6 minus 2. Right, so how do we go about this? So I'm just writing this x1 plus 3x2 less than equal to 0. Right, I hope I'm right. It's basically saying y equals to minus 1 by 3x. So how do we go about this? I hope you can hear me now. Okay. I think there's an echo. Can you just please check on Sonia? Hello?
Am I audible?
Yeah.
Yeah, I just lost my connection. Sorry about that.
Yeah, no issues. So anyway, I was just saying that this is my this is the line, and my concern is this thing exactly less than equal to 0, which means I am in this region. And I have some function, some cubic function, and I am looking at this point 6 comma minus 2. So yeah, so first of all, does it belong to an obvious check? So I want to see whether this constant qualification holds at this point or not. Right, so true or false we want to see. So what do we do?
So just substitute in the equation and see events.
Yeah, so right now x1 plus 3x2, so we have x1 star plus 3x2 star. It's nothing but 6 minus 3 into 2, which is 0, and that is clearly, so that means constraint is active.
Yeah.
Okay, good. So constraint is active, that means what do we need to check? This implies either, so let me write it slightly, let me specifically, g of x is x1 plus 3x2 is active. Okay, so that means either gx star or the gradient of gx star transpose t less than 0, or gradient gx star transpose t equals to 0 and g is affine for some d. So here what do we have? We have clearly a case of affine set, right?
Yeah.
Okay. Is it affine?
Yeah, it's affine, right?
Okay.
100% affine.
Right, but let me just still go ahead with this calculation without, so I'll not worry about this part right now, the equality or less than. I'll just evaluate this inner product. Okay, so what is the gradient at this point? It's nothing but 1 comma 3, right?
Yeah.
Okay. And can we find some d such that we can make the inner product to be 0?
Sure.
Okay, so we can just take what can we take?
Minus 3 1.
Yeah, exactly. So we just take t to be minus 3 1. This will ensure that gradient linear product is 0, and since G is affine, well, since G is affine, what do we have? CQ1 holds.
CQ1 holds. So D is just any direction, right? Not equal to 0.
Yeah. For some D in Rn. So here it's
which is not identically 0, right?
Yeah, otherwise it's trivially true, right? So we want something that is not 0. Okay, moving on to question 3. So question 3 is saying that again we have a 2D optimization, 2D variable x1 square plus 5x2 square such that 2x1 squared plus, so yeah, these are my constraints. Right, so the question is, which of the following, so I'll just mention the candidate points in a minute, but we are looking for Slater points.
Deep, I have a small question.
Yeah.
So these various CQs, are they on an equal?
No, CQ1 is a sufficient condition for the standard CQ to hold.
Standard CQ means which you have learned before, right? In the week before.
Standard CQ is what we saw here.
The gradients are linearly independent, right? That one.
That is again a specific case, but more generally, all that we are saying is, where did it go? Yeah, this that I have written here. So more generally, when we say this, I think I deleted for M constraints. Yeah, I think I deleted that. But when you see this tangent cone as an intersection of corresponding tangent cones for all the M constraints, right?
Yeah.
So we get this for each constraint, right? Gradient Gi x star d less than equal to 0. And in case of equality, we get the inner product to be exactly equal to 0.
Yeah.
So yeah, sorry. So I'm just saying that just a sufficient condition for this to hold.
Okay.
So what you said, linear independent constraint. So that is one way to ensure this, right?
Okay.
So I'm sorry if I was not clear earlier. So yeah, the linearly independent constraint qualification that you mentioned, correct. That is one sufficient condition to ensure this. Another way to do it would be to simply say this, what we have mentioned here, CQ1.
Yeah. Okay.
Yeah, here that I mentioned, CQ1 holds if for the active constraint I can always find a direction like this.
Okay, so either CQ1 or the LICQ, all of them imply linear constant qualifications, right?
Correct. Yes. So the thing is, constraint qualification is something that we desire. Now the general form, the tangent cone being equal to intersection of these tangent cones. Now what conditions would ensure that form?
Okay.
So that's what we are looking for. And in this case, by the way, you can see in this case, by the geometry of the set, what will be the gradient at x star? Yeah, so the gradient will be this, right, at this point.
Yeah.
So we can find an obtuse direction, right?
Yes.
Yeah. So similarly, okay, this is not an affine case; it's just a convex case. So you see here, right? The constraint qualification actually holds. In fact, we just proved that. Although we proved it using geometric arguments, but there's another way to see it.
Yeah.
Does that make sense?
Yeah, it makes sense. But obviously the cases of constant qualification becomes more non-trivial when we have multiple constraints, right?
Correct.
Then only when these things makes more sense. Right?
Yeah. So then it becomes difficult to verify it by visual inspection.
Yes, that's my point. Yeah.
Yeah, but this is at least confirming what we wanted. So in this case, like I was saying, if you can find an obtuse direction, a direction which is at an obtuse direction with gradient, then we saw and we also proved it in a different way that yeah, indeed the consent qualification holds. So these are all, whatever condition we are coming up with, these are all sufficient conditions.
Yeah, I get that. But my only one small doubt is remaining: why we have multiple flavors of constraint qualification? How do they help?
That I am. I'll have to check on that. I'm sorry. I'm not aware of which conditions are suitable for what types of problems. That I am not
Yeah,
sure.
means since we have multiple constraint versions of that, means there is nothing, not one version that works across the board, right? There should be some reason across,
Yeah,
means
yeah,
like that probably.
yeah. I mean, just off the top of my head, for example, in LICQ, I need to check the linear independence of the gradients for all the active constraints, right? So
Yeah.
so I'm just thinking out loud. So maybe, for example, this is not always feasible to do.
Yeah, that's
This is
what
this is
means.
an expensive step. So maybe, um, again, I'm not able to think of any explicit example, but maybe checking this is perhaps easier.
Yeah, since we have many flavors, the utility of them will come when one is easier than the other, right? In specific circumstances.
Yeah, yeah. But maybe I'll check and I'll try to get back to you. I have to read up on this. I'm not sure which ones are
Yeah,
preferable.
this is just a very natural question that came whilst I was listening to the lectures. Yeah.
Yeah. So yeah, thanks for the question. So question is, which CQ X, I'll say, no, which condition to use to ensure CQ? For example, when to use CQ1 versus LICQ.
Yeah, just any two will suffice to illustrate the point.
Yeah, yeah, I'll check and I'll get back to you on that.
Yeah, sure. Thank you.
Okay, so let's get back to the question. So the question is, for this optimization problem, here you have quadratic and linear constraint. The question asks us to find Slater points. Okay, so the options are as follows: 0 0, 1 0, 0 1, and 1 1. So what is the Slater's condition? Do you
Yeah,
remember?
status condition is, means if I can remember correctly, we have to find an uh, x hat such that that lies in the feasible set, and it follows with strict inequality. Means if I remember everything correctly, I do not know whether I remember.
Uh, yeah, I think I didn't catch it properly. I'll just mention it here quickly. So
Yeah,
what we are saying is, if we are interested in the candidate point x star in this feasible region, okay,
yeah.
then we call this uh, for this um, just a second.
And the,
Yeah,
just allow me 1 minute. I'll just change another headphone. My battery has drained down.
yeah,
Just give me
sure,
1 second.
yeah.
Hello?
Yeah.
I am audible, right?
Yes. Yeah. So Slater's condition. What we will do is, first of all, we are at some point in the feasible region. That is going to tell us at that point in the region what are the active constraints. Okay. So we'll call that set script A of x star. Now we are saying that if there is a point x hat such that for each of these active constraints, we either have in a manner similar to what we saw in CQ1, but instead of the gradients, all that we are saying is either the constraint is convex and is inactive. Okay.
Yeah, this is a definition. Yeah.
Or I am saying that g of x less than equal to 0 and gi is affine.
Yeah, I mean, see, this is a Slater's condition. Can you? This is the direction of implication exactly that that this implies CQ1 and CQ1 implies this.
CQ1 will, I think CQ1 will imply CQ2.
Yeah, that was said in the lectures, but is the implication the other way also true?
No, I don't think so. I don't think so.
That eventually means one is weaker than the other, right?
Yeah. So maybe there are counter examples, but I am not sure. I just know that CQ1 can imply CQ2 for the simple reason that I can take that x hat minus x star as the D in my where is it? Yeah, here.
Yeah.
This D, if I can take x hat minus x star. That should be giving me, so G is convex, I think. Yeah, G is convex, so I can use this property that G of x is greater than G of x star plus x minus x star transpose gradient. So I think I can just use this.
Yes, you can get that. That will means that will mean that okay, that will mean that Slater conditions will imply CQ1, right?
No, CQ1 will imply Slater's condition.
Sorry, CQ1, yeah, because CQ1 can imply the Slater condition. Yeah, true. Yeah.
Okay. Right. So then x hat is the Slater's point, and the constraint qualification holds at x star. So x star, where is it coming? So x star is actually the point we are interested in.
Yeah, the point in question, right?
Yeah, that will give us the set of active constraints.
Yeah.
For those active constraints, we just hope that there is at least some point. Some point x hat such that either we are in the interior of the constraint or we are on the or we are on the surface, the affine surface. I think this should be equal to here. It's redundant. If it is gi is affine, then
yeah, that's what I was thinking. It should be equal to. Otherwise, it becomes meaningless.
Okay, so then this is the Slater's point, that x hat is the Slater's point. So we have existence of such a point, and then we can say that the point of our interest at that point indeed the constraint qualification was. Okay. So the question is not asking for us to so we are not given a candidate point x star. That's what I'm trying to say. Instead, we are just looking for this case, what are the possible Slater points, given that these are the constraints. See, because this condition, I could check for each and every constraint, right, depending on whether it's convex or affine. For that Slater's condition, I just need to check this holds for the active constraint. So I'm not bothered about that right now.
But how do you know the constraint is active without a candidate point?
No. So so that's what I was saying. The X star here, the only way it plays a role is it gives us the active set. The evaluation of the constraint, it happens at that X hat, not X star.
Okay. That doesn't depend on X star,
Yes.
right? The X hat.
Yes. So if here we are given all the X hat. All we need to check is this is a convex constraint. This is a convex constraint. I mean, this is an affine case. So all that we need to check is whether it actually 1 second. I think g of x should be okay if it is less than equal to 0. This is okay. So remember that we are not asking x hat to be some feasible point only. Can be any Rn point. Is that fine?
Yeah, I get it.
Okay, so
Yeah, this definition is a little bit tricky and hard to digest in first go.
Yeah, it'll take some time. Anyway, let's see. We'll solve some problems and we'll get more better. Okay, so in this case, yeah. So we just hope that either it's strictly for less than 0 or it is less than equal to 0. So for each of these points, what do we have? So in case of A is 0 0. So what do we have? So okay, let me maybe write.
So here all the are affine, so we only check for the second condition, right? Because
No, the first one is a quadratic case.
Okay. This one is a quadratic.
Okay, and second is the linear constraint. Okay, yeah, right. So these are the G1 and G2s that are given. So first case, the point is x hat is 0 0. So what will that give us? G1 of x hat minus 7, G2x minus 5 less than 0 less than 0. So A is okay, right? A is a Slater's.
Yeah.
So it's just a matter of checking this. There's nothing to it.
Yeah, this is very
Okay, so similarly here you can get minus 5 and it should be minus 4. So okay, what happened? Yeah. Okay. So yeah, we can just keep doing this. And same goes for 1 1.
I think, hello, am I audible?
Yeah.
So I think I mentioned all as 4 as correct, but it came out incorrect, I believe so.
No, all 4 are fine.
All 4 should be fine, right?
Yes. So here if you check for 1 0, 1 0 anyway checked, 0 1 and 1 1 are the ones left. So if I put 0 and 1, I am getting minus 2 and minus 2. And if I'm putting 1 1, then this is 0. This is 0.
Yeah.
Okay. 1 second.
I think I got it.
Oh, okay. Sorry, I made a mistake in writing. I'm extremely sorry. This is 2 plus x1 x2 squared. Sorry. So in that case, if I put 1 1, so this is 3 minus 7 and this is 4 minus 5. So in every case there's a strict inequality. So it's fine.
Yeah, it's correct. Yeah, sorry. Yeah, everyone is a Slater point. Yeah.
Okay, so let's go to the next question. So the next question is saying dual function of a minimization problem is a convex function. So is this true or false? So what is the dual function?
Yeah,
It's
so
nothing
dual
but the
function is
unconstrained minimization over x of the Lagrangian, right?
Yeah.
Right. So and what is the Lagrangian? The Lagrangian is nothing but
the objective plus this thing.
Yeah, so the objective plus lambda I g I of x mu j h j of x, right?
Yeah.
Okay, so the question well, the claim is that this dual function is a convex function. Convex in what? Well, here the arguments are lambda and mu. So what do we want to look at here? Whether it's convex or concave, what do we want to look at?
So the question asks whether it is a concave, right? So
the question asks whether it is convex.
Yeah, it's a concave function. Whether it's a
Yeah,
concave
but how
function,
do we prove that? So what do we want to really look at is theta lambda prime plus 1 minus theta lambda prime lambda double prime theta mu plus 1 minus theta mu prime and okay, let me keep life simple by being just one of them. Yeah, we want to look at this quantity, convex combination, right?
Yeah.
And you want to say whether it's greater than or less than equal to. That's what you want to check. So yeah, what will this be? Infimum x Rn of x plus let me take a shortcut. So what I will do is, let me know if this is clear or not. I'll just write it directly. So just to clarify, what I've done is I've written this as, here there is a factor of 1, right? So I've just written as theta plus 1 minus theta, and then there is a theta plus 1 minus theta. So this theta for 1 theta we will get this summation. Similarly for 1 minus theta we'll get a similar summation. So I'm just doing that. Yeah, let me not write that directly.
I was just thinking out loud to myself.
Yeah.
So can you use some basic properties of convex sets to prove the rather than using the formula itself?
Yeah. That will be great. Yeah. So we can do that also. So maybe we just look at both the ways.
Because in some questions writing the formula may be tedious and you want to get a quicker answer quickly, probably.
Yeah, I mean absolutely. So that's definitely true. We can do that. So yeah, what can we say in this case?
So the infimum over this, yeah. So yeah.
Okay.
Theta is less than 1 minus theta plus.
So what we are really having is infimum of P of x plus Q of x over x. How do we relate it to infimum plus infimum?
Yeah, that's the crucial point. Yeah. So infimum of px is this. Yeah, this should be just give me a second. Yeah. This is less than equal to, right?
Which one is less than equal to what?
Left hand side is less than equal to the right hand side, right?
And why is that?
Yeah, because qx can be negative, right? Which subtracts from px. So that means if you take the if you take the infimum on the left hand side, it becomes less than the individual infima. As I was just thinking, may not be correct also.
Yeah, I mean it's slightly long here. You'll have to take a few different cases and do it. So I'll just I'll skip this for now. I'll just lead to the result that indeed what you can try doing is it's like you would expect. It is sorry. T x lambda mu plus 1 minus theta. But more importantly, and a much cleaner way to do it would be like you were suggesting. So I could look at this definition and can I say something from here? So I want to see whether it's convex or concave in these arguments, lambda and mu. So here let's say I fix this infimum x. Infimum over these x, unconstrained optimization.
No, fix this means fix a x, right?
Yeah, fix a x, right? I mean here for a given x in this side, you fix the x. So this is a constant. This f of x is a constant. Hj is a constant.
Yeah, then it becomes an affine function.
Yeah, then it becomes affine in this, right? So what can we say based on this? So like pictorially, if you were to say, if you were to look at what will it look like? I'm just giving a pictorial way of looking at things.
So we should all consider the pointwise minimum, right?
Pointwise minimum, correct?
No. I am misunderstanding the levels here. Axis. The axis here are theta and mu, right? Hey, lambda and mu, right?
Yes. x is fixed. So for a given
x is fixed.
yeah.
Okay.
So I mean here all that you're trying to say is just fix an x. What does this look like?
Okay.
Then it is affine in lambda and mu, right?
Yeah.
So this will be for each lambda and mu. So some affine things going on. So how will it look like? I mean here maybe the way I drew it, it will be neither probably, but it'll be something like this, right?
Yeah, the least upper bound, right? The greatest lower bound, yeah.
Yeah, so just to infimum x, let me write what do I want to say? I want to say gxyz affine in yz for every x. So how do I write that then?
It's an intersection of these things, right? So, but
I mean, how do I write it?
So it will be like x transpose y, right? The representation.
No, so it can be as general as this, right? For example, this complicated function is affine in lambda and mu, lambda is and mu j if I fix the x. But in general, it's a very complicated function, right?
Okay, yeah.
Okay, so I'll just leave it here for now. Just try it out. This will be a good exercise to maybe show concavity, convexity of functions. If it doesn't work out, maybe I'll just briefly prove it in the next class. Okay.
Okay. But it's possible to do it this way, right?
Yeah. So this is a cleaner and general way to do it. Here you'll have to break it into many cases. And
so how many cases it will be? Many cases means first is positive, second is like that, right?
Yeah. So yeah. Let me just focus on this right now. We will come back to it if you want. Okay. Let me just write this down. Point wise. Infimum of affine functions equals to concave. Therefore, claim is false. So I just request you to try proving this, and if you do this, then that's really the blueprint you would follow for argument here.
Okay.
So just try it out once.
Claim is false. Yeah. Okay. No, but the claim asks whether the dual is a concave function, right?
No, it's for asking for convexity.
I think the Lagrangian dual function is a concave function. That is the claim. State true or false.
No, the question asks dual function of a minimization problem is a convex function. So the claim is false because it's a concave function.
Oh no, I believe you are question 4 or question 5.
Question 4.
Question 4 is state true or false. The Lagrangian dual function is a concave function.
Okay, the copy that I have in that it is clearly stating the other way around. But anyway, either way, the answer hopefully is clear, right?
Yeah. Means it's no problem, no issues. Same.
So I have an unconstrained optimization case. I am looking at an ellipse. this linear constraint. I mean, it's fine and it's a convex constraint. And how many variables in dual function? Oh, why did I write x1 x2? X plus 3xy plus 3y, sorry. So it's just one, right?
Yeah, this is just one constraint.
Yeah, because there's
Lagrange
only
multiplier.
one constraint. Okay. So in the question 6, what we are given is, so let's just state the problem first. Minima is x, f of x such that g of x less than or equal to 0. So both f and g, they are going from Rn to R, and so it's a single inequality constraint. So that means the dual function is d of lambda. There's only one variable, and we are told that t of 3 is 10 and t of 5 is 20. So which of these is a valid value of t of 4? 8, 10, 16 and 12. So how would we go about this?
So Jill, just use the concavity property of the dual function.
Yeah. So is concave. This implies lie above the average of d3 and d5, right? By definition.
Yeah.
So this implies 16 is possible. Okay. I think we are still in the same setting. So we have x in Rn. Oh, it's a multivariate case. Okay. So the same form, but here we have multivariate case. F G R into R. D lambda is the dual as usual. Claim is x star is optimal. Then there exists a positive lambda such that t of lambda is strictly greater than f of x star. So how do we go about this here?
Just give me 1 second. No, this way used a weak duality, right?
Yeah, so just
Yeah,
to
yeah, yeah.
state it a bit more explicitly, so here we have for all lambda non-negative, we have L of x star, the Lagrangian, to be less than upper bounded by f of x star, right?
Yeah.
And d of lambda is what? Infimum x Lagrangian, right?
Yeah.
So d of lambda less than equal to L x lambda for all x, sorry. Okay, so that means d of lambda less than equal to L of x star lambda, which is less than equal to f of x star for all lambda greater than equal to 0. So claim is false clearly. So everything okay so far?
Yeah,
So
yeah.
except for this one thing which I just asked you to prove, just try it out once. Okay?
Yeah, the affine function, right? The infimum.
Yes. So this is one thing which I haven't done, and there's one more point about which
Yeah, the
conditions to use to ensure constant qualification and
the
when.
constant qualifications.
Yeah, so that is one homework for me, one homework for you.
Yeah, yeah, sure. The Fenchel dual you need to explain. I'm not understanding the concept of Fenchel dual.
Yeah, I'll explain.
Conjugate dual.
Yeah, I'll explain. Let me just write it down. So okay, uh, so when we
No, no.
have, so let's say this is our function y equals to f of x. So how will we represent this function? What is one way of the usual way of representing our function? Let's say any point on this graph. It just give the answer. Okay, the one way to represent this function would be by the graph, right? X comma f of
Yeah,
x, right?
yeah,
So this is one way of representing my function.
yeah.
Alternatively, what I could do is let's say at a given point, let's say I'm here, this green point. I hope you are able to see the green dot here.
Yeah.
So
I can
let's
see.
say I am at this point. Let's call it x hat maybe. And let's say I told you the slope at this point. So let's say I gave
Okay.
you the gradient f of x hat. Okay.
Huh.
And what I'll do is I will just draw. So I'll just extend this. I'll just extend a tangent from this point. I'll take this intercept. So secretly it is f star of f of x hat. No, sorry, f star uh, of gradient of f x hat. So let me actually not even do that. Let me just put this as c. So I hope so far you're with me. So there is a point here x hat. I know let's say I have access to the gradient at this point.
Okay.
So I'll just extend a segment and I'll basically find the intercept, which is, so
Okay.
what I'll do is I'll draw a line which is having slope of gradient f of x hat at this point, and I'll look at the intercept accordingly for this line.
Okay. Okay. So this works in all cases, like if the function can be of either any shape, right?
Yeah.
Like
In general,
orientation.
it can be anything, but when we do analysis, we generally tend to use this for convex functions.
Okay, fine.
So, it's still not complete. I just finished the first step. So what do we do now? So remember that I want to define this graph. I want to define this function.
Okay.
Okay, but I don't want to use this representation x comma f of x for all x in the domain of f.
Okay.
I don't want to do that. Okay.
Okay.
So instead, what I'm going to do is at all the points in the domain of my function f, this x, right, all these x, valid x, what I'll do is at each point, what I'll do is I will tell you the intercept and I'll tell you the slope.
Okay.
So what I'll do
slope
is
means basically a direction you are telling me,
yeah.
right?
So what I'll do is and I'll take a envelope of this. I mean, the drawing is poor, but I hope you get the point.
I get the point.
So what I am really doing is at each point I'm finding a linear underestimator that just touches it, and that is represented by my slope of the function at that point and the intercept. And the intercept, how do I find this f star y? So this c that you are seeing here is really the intercept at this point. What should be the intercept of the line, so that I can draw this linear underestimator which just touches at this point, which just touches the function f of x at this point exact.
Okay, so it's a universal linear under approximator, all x in the domain.
No, this is for a given x.
No, I'm telling for a given x, this is a okay. This is a linear under approximator to the function. Okay, get it. Yeah.
See, I'm just drawing an envelope for this function. So basically, let me just to conclude. So either you represent it by this representation x comma f of x, or what you can do is you can give me the slope and you can give me the intercept. So I'm basically giving these lines.
Okay, you're specifying lines. Yeah.
Okay, and then I take a envelope of this.
Because the infimum operation, right?
This will be the max operation here in this case.
Okay, this will be max operation. Okay.
Actually, do I need to say that max operation?
Yeah,
take the convex envelope of think max operation should be involved. Okay, I think it should be a max operation. Infimum doesn't make sense here, but
yeah, the infimum doesn't make sense. Yeah,
I draw these and yeah, I think it should be a max operation, and I basically get this.
So this is basically another representation.
Yes,
right?
It's just another way to represent the function.
And then the next natural question is how it helps.
But that will be a bit difficult to explain without doing some convex analysis. So I think that will then distract us from the topics of this course.
But it's helpful, right? Representation.
Yes, in general, it definitely helps a lot in many in analysis of many optimization questions.
For me to dig this up. Okay.
Yeah.
Okay. Good. So it looks a bit like the Legendre transform that we use in physics. Is it?
It's related? Exactly that. I mean, transform I don't know, but this is called a Legendre.
Yeah, the same thing. The Legendre transform. Yeah, which you used in thermodynamics and all statistical mechanics.
Okay, I mean I'm not familiar with that, but this thing is called Fengel conjugate, and there are these functions which we use, which are called Legendre functions. Whenever we are studying these types of conjugates,
I think it's the one and the same thing then. Yeah.
So I mean, just be careful. So maybe what you are saying is the function f, that may be the Legendre functions that you are talking about, which are like. So basically, Legendre functions, again, just to maybe a slight digression. So they basically have this type of a behavior. So what they are these strictly convex functions, and they keep on growing as you go farther and farther away from the origin, like a well, like a bowl.
Okay.
So maybe that's what you are referring to. I'm not sure. So for those functions, a lot of times when we are computing these duals, these Fenchel duals, so we compute that for lot of times when you do analysis, we compute that for Legendre function because those are all nice convex functions. And the nice thing about convex functions is if you take dual of a dual, that is the function itself.
Okay.
So, but yeah.
The dual here refers to the Fenchel dual, right?
Yeah. So this thing is called Fenchel dual.
Or maybe sometimes also the conjugate dual, right?
Yeah. Or they also call
get this
Fenchel
now.
conjugate. All variations.
Yeah. Yeah, all over the place. Yeah, I get the basic point now. It's much more clear because I was stumped by this definition.
Yeah. Okay.
Yeah.
Right. So here also, by the way, when you see, it's a nice bowl function that we have picked here. So generally, we take these functions to be these strictly convex functions because there we get the desired property of the dual of a dual being the function itself. Okay. So right. So we want to find f star 5. So how do we do that? We just apply definition.
Y transpose
F star x. Sorry, I made a mistake.
I think this x is that there is a wrong in the printing. I think here.
Yeah, I'm not sure, but I definitely made a mistake. So here we should be looking at x. So at a given point, what is the intercept? Similarly, you fix x basically, and you vary the y. You vary the slope.
Okay.
Okay, so you have yx minus fx, and here you put x equals to 5. So what do we get? 5y minus, what is it?
5 it's 50. It's
okay, just a second. Okay, I think I'm making a mistake. I think I am mixing up things. Just a second. I am given a slope. Okay. Yes. So that means correct. Sorry. Yeah, my bad. So this is fine. Okay. Yeah, sorry about that. So what I'm given is again going. Okay, I deleted that. But if you remember, either I represent by x comma f of x, or what I do is I give what do I give? I give a slope, right, and a corresponding intercept c. Okay.
Yeah.
So this c is basically my f star, this intercept, and I am given some slope. Okay. But I need to go around the domain of f, where I am able to match that slope so that I can find that appropriate intercept.
Okay.
Okay, so I'm sorry about this.
Then you are scanning through the x's, right? All the x values, right?
Yes.
Then supremum over x, right?
Yeah. Okay, and the thing is, this is an unconstrained optimization problem. So here we just do our usual analysis. So
just take derivatives.
Yeah, so x star I think should be 5 by 4, yeah, 1.25. And yeah, so x star is 1.25. And this is concave, that you can just check from double derivative test. The double derivative is simply minus 2. Okay, so it's a concave function, and this is it's a minimum, local maximum, local or global, doesn't matter. So concave function. So what is f star 5? Simply 5 into 5 by 4, or
Hello.
I'll just write 1.25 minus.
Hello.
Hello, yeah.
Hello.
Can you hear me?
Hello.
Hello, I'm able to hear you, Soumyadeep. Can you hear me?
Yeah, I think I lost you for a couple of seconds. Hello.
Okay, I hope you're able to hear me now.
Yeah, now it's clear, but I lost you for a couple of seconds.
Okay, yeah, I think there is some lag. So can you see my screen and can you see my pointer now?
Now it's back to business as usual.
Okay,
Yeah.
okay, fine. Yeah, so I was just saying that it's a simple unconstrained optimization problem, and this is a concave function. So whatever candidate we found, we can just quickly check that this 1.25 point is actually a global maximum. And so that means you just plug the value, this supremum is actually attained, you just plug this value, it's a finite value. And that finite value turns out to be, I think, I don't know, around 3.1 or something.
Hello, Deep.
Yeah.
Let me do one thing. I'll just log out and log in. Just give me 1 sec.
Okay. Yeah.
I'm not able to see the screen.
Yeah, sure. Yeah. Hello, Soumyadeep, can you hear me now? Can you hear me now? Hello? Hello, Soumyadeep, can you hear me? Okay, yeah, lots of technical glitches today.
Hello?
Yeah, can you hear me now?
Yeah, I can hear you. Am I audible?
Yes.
Yeah, today there is a day of bad glitches.
Yeah, no issues. Anyway, we just go slightly over the time. I hope that's fine. You just finish these 3 questions and end the session there.
Yeah, sure.
Okay. Right. So the next question. So anyway, I think we already discussed it. Just a computation problem, and I hope I was able to convey the intuition. So we are just representing the function with an alternate representation using the slopes and intercepts.
So this works also for more complicated function, right? Without a bowl shaft and with many minima and maxima, they also work.
Yeah, we can do that. We definitely can do that. So because here, if you notice, for a given x, this is linear in y. Right? So it's just a soup over linear functions. So it's a concave optimization problem.
Yeah. Okay.
So these are nice optimization problems, but the thing is, the kind of analysis that you typically do with these functions, you would want the f to be somewhat nice. If you pick up any arbitrary f, let's say some complicated non-convex function f, it won't give you the desired properties. But I have not told what the desired properties are and why they are desired properties. So that will be a bit of a digression from this course material. Maybe we can discuss that offline if you like.
Got it. So there is a lot of pushing under the rug here going on.
Yeah.
Okay, get it.
I mean, he just the instructor mentioned this because we were talking about duals, so he just wanted to clarify that we are not talking about these duals.
Yes. The use cases he didn't speak of. He just mentioned this in passing.
Yeah.
Get it.
Okay, so question 9, what we have is our usual optimization problem minimize fx such that there are some m constraints. Okay, and we are given the set G. So here remember the comment that to understand this optimization problem, what we will look at is the joint space where the variables correspond to the constraints, and our, of course, the optimization variables which is x. Okay, so what we'll do is we will go to that space. So that's what we are defining, that space which we want to traverse.
Just one small question.
Yes.
When you are defining so obviously we are relaxing the constant, right? Instead of less than equal means we are defining a t and then we are defining an u. So we are relaxing some of the constraints, right? So that helps in defining the dual space in a sense. Means I was little bit unclear about that.
I am not sure if that analogy will go through. Let me think. So what you're saying? Can you repeat that?
Yeah, I am saying that suppose we are given that minimize fx, but
Right.
when you are putting fx less than equal to t,
Right.
that means this constant this consists of we are somehow expanding the class of problems, right, to consider. So
Right.
so instead of suppose the constraint says gi is x is less than equal to 0, but now you are putting an arbitrary value ui.
Yes.
So somehow you are broadening the class of problems, right? So in a sense, does that help in defining the dual space? It means the joint space of the constraint and the problem itself. That's my question. Basically, if I'm not able to express myself more clearly.
So yeah, I'm not sure if I understood the question correctly, but yeah, let me see what can we say. Help, like, can you elaborate what do you mean by help? Define that dual problem.
Help. I mean, it helps us to visualize the dual space and the problem space in one go. That's what I meant. But it helps. Like means we are defining one tuple of u and t, like u, v, and t, right? So that somehow defines the dual space. So that was my question. Means
no. So that's the thing. So what we want to do here is not define the dual space. What we want to define here is a space that somehow captures both the dual, the feasible directions. Sorry, not the feasible direction. Feasible set of the dual problem and the primal problem.
Yeah.
So think of it like we are lifting the problem, so to speak, such that we are now looking at this tension between the variables corresponding to the constraints and the primal variables.
Yeah, because anyways, the definition of G just indicates that he just want an existence of an X, whatever be it, right? So that means he satisfies the primal problem.
No, so G contains all such points that would be of interest to us because we want to, let's say, solve this problem which is primal P. So what I'm saying is any point 0 comma t infimum of this, let me write it properly, infimum this is what we are interested in.
Okay, these are subset of the space G.
Yes. So we are only interested in all the points where this component is 0. This component we are going to find the minimum such value. Because just look here at this f of x less than equal to t. We want to minimize this so that.
Yeah, this is evident, pretty evident. Yeah.
But beyond that, all that I see is depending on the geometry of your constraints and of your objective function. If you how do I put it? Let me see. Yeah, it's a bit hard to give a picture that's not misleading. If I just give a toy
Yeah,
example, then
no, yeah. It should be realistic also at the same time. Yeah.
yes. Yeah, I'm not sure. I'm still thinking. Maybe
Yeah,
I'll get
yeah,
back
it's
to you.
bit currently in terms of the two spaces. Yeah, that's what.
Yeah,
Means
it's like I just want to
I
look
was
at a
thinking.
space where I look at the values that like for example here when I mean I'm probably just repeating myself, but here for example, if whenever I'm solving this problem, I don't really care about what happens to the corresponding values in the dual space, right? So I'm just seeing that I'm just looking at these points in conjunction. I'm lifting them into this higher dimensional space, and then looking at these points in conjunction and seeing if I can say something about the optimal value that this problem attains versus the value that the corresponding dual problem attains.
Yeah, yeah,
It's like
yeah.
saying that this is just one way to keep track of both the primal and the dual values.
Yeah, sort of. It releases the tension between the primal and the dual spaces,
Yeah.
in a sense. Yeah, yeah. I get it. I get it. Yeah. Like for example, fx less than equal to 2 looks like it's like a cone kind of object.
Uh, okay. So here you are saying x is fixed, is it?
Yeah, so yeah, x is fixed. Suppose we have a standard representation of a cone, higher dimensional cone, right? X less than equal to t. Then xt combined together as a tuple.
Okay, I don't think in general you can say that because uh, for cone you are saying okay. So you are
I think
saying
not cone. I think it's a norm cone.
okay. So one second. So you are saying this t greater than f of x is some constant. So
Yeah.
you have a set t such that t greater than c. Okay, can you just please help me remember the definition of norm cone?
Yeah, I think norm cones means the suppose you have an x, then you consider means and you consider the all tuples of xt such that x less than equal to t. If I remember correctly,
Uh, Consider
Ju-
x such that.
just give me a second. I'll just pull it out. I have void in front of me. I'll just pull it. So I was just trying to correlate this definition with these things. That's all I wanted to uh, see. So the second order cone,
Hmm.
for example, is a norm cone for the Euclidean norm. That is, xt belong to Rn plus 1 such that the Euclidean norm is less than equal to t.
So what is this t here? I didn't get it.
T is any particular real number.
Uh, oh, no. Okay. So are you saying that the name of the set?
Yeah, this set is the norm cone.
So what I've written here is this what you mean?
This is a second order cone actually.
Uh, okay. So
Second
for
order cone
right.
for if you consider an R2, then the second order cone will be in R3 as usual.
Okay, I see. Yeah, I think I do. Okay. Okay, but I don't see why this should be a cone. Cause let's say t greater than equal to half. Uh, so if this is a cone, if I multiply by lambda, they should still also remain 1 by 2, greater than 1 by 2, right?
Yeah, from the definition.
But then that
But
won't hold true.
but that won't hold true. Yeah, for unrestricted lambda. Yeah.
No, any non-negative lambda, I could just
Yeah,
make it 0, right?
yeah, it doesn't hold. Yeah, yeah.
So yeah, I mean, I think in general it's hard to say what this will look like.
Yeah, means it's difficult. Yeah, means I was just thinking out loud. Yeah, leave that. Yeah, we'll come back to the.
Yeah. Okay.
Some other time.
Okay.
Yeah.
So this set is given to us. So this is very in a manner similar to how we have defined in the lectures, and the claim is that the set G is convex. Any thoughts on?
Yeah, this should be true, right? Because it's already proved during the lectures itself.
But I have a slight problem with this question. So this is true. That's true. Only if, or maybe I'll just say this. Not only if
the
that
GI, the constraint should be convex, right?
Yeah, GI for all I and F convex. This
Yeah, that should
implies
be convex.
G is convex. That is missing in the question description.
Yeah, that's what is. I did not answer the question because of that very reason.
So claim is true under star, and I will just call this as star. Okay. Alright, so last three questions and then we wrap up. Okay.
Yeah.
So again we have a 2D unconstrained, not unconstrained, sorry, 2D variable. Okay, lots of typos here.
So there is a typo here, right? Yeah.
Yeah, so it's a three variables. And so we will define G as above. So the G that we defined here, this G. So there are how many constraints? 3 constraints and 1 for this. So I think G will be a subset of R4.
Yeah, R4.
Okay, that was the question. Okay.
Yeah, that was the question itself.
Okay. So K equals to 4 because 3 constraints plus scalar valued objective.
In the lectures, Professor Kulkarni mentions it at UVT, tuples of UVT. U for the inequality, V for the equality, and T for the objective, right?
Yeah. So I mean here also the equality we can just convert it as inequality, right?
Yeah, but then you need 2 of them, right?
Oh yeah, you are right. Correct. Then it should be 5.
Yeah, that's what I was confused between those.
Okay,
How do you means which you want to define it as a equality or 2 separate opposite inequalities?
Right. Yeah, I think you are right. Fair point. But anyway, we as long as we understand the concept here, it's okay.
Yeah. Okay.
So we'll just take it that they mean the UVT formulation. So.
Yeah, that's what it's not mentioned.
We are having this optimization problem where we are minimizing the norm of this vector such that AX equals to B. Right, so A is given to, okay, so this is not mentioned here, but let me ask this. This is something very simple and very important that I feel like sometimes gets omitted. But is this problem even well posed?
Minimize x1 square plus x2 square such that ax is equal to b.
So I'm not saying that minimize just this. That is of course well posed because you can just the minimum value 0. But I'm saying subject to this constraint. And like why would I want to pose a problem like this? And you can think of a situation where I would want to basically minimize norm squared such that ax equals to b. Why would I want to formulate a problem like this? Any thoughts on that?
No, I'm not getting any clearer picture.
Okay.
It looks like very artificially posed. Means
no. So there's a reason for that, right? So the reason why we do this. And we'll make an assumption. Now can you say?
The pseudo inverse.
That's okay, but what's the rationale?
When you are over determined system, you want to find the least norm solution. Is it like that?
Yeah, but why does it have a solution in the first place?
Because we have only two variables, right?
It's a fat matrix, right? Yeah, exactly.
Yeah, it's a fat matrix. Yeah.
So solution always exists. Point is
it's under determined system. Yeah.
So it's okay, right? So we'll have solution. Null space is not trivial. So one criterion is to just pick the minimum norm solution. Okay.
Yes.
So that's the reason why we solve these problems. So here we assume that the solution exists, but then there is a counterpart which we solved in one of the first, I think, second or third week discussions, where we had a setting where you are minimizing norm of ax minus b.
Yeah. I remember that.
And why do we solve that question? Why do we solve for such optimal problem? Because here, actually, B does not belong to the column space of A.
Yeah, I remember.
So here what we have is A is full column rank.
Yeah.
And why is that? So here what we are really saying is, if this is your column space of A, and this is your B, okay?
The projection of B you want.
Yeah, so we want to find point on this column space, some B hat, such that E equals to B minus P hat is orthogonal to
B yeah,
hat.
Correct.
I mean, it's orthogonal to a vector here, B hat.
Yeah, this is what we do in least square solution, right?
Yeah. So that this is the least square. So I'm just saying that there is a reason why we formulate it like this. It's not just for the sake of writing it.
Yeah, get it.
Okay, so let's say the optimal value for this optimization problem is P star. Okay, and so true or false, the following statement that we need to determine. D star optimal value of dual, then E star equals to D star. Is this true, false?
I answer it as true. I have also written the solution somewhere. I'm not able to locate it. Somehow I've reasoned my way. Just give me can you just give me 1 second? Just 1 second.
Yeah.
Pull up this. Yeah, I think I have written it down somewhere. I don't know. I written rank is a full row rank. After a while, I have reasoned somehow. Yeah, let's go through. Yeah, let's go through the proof.
Yeah, so you're on the right track. So A is full row rank. Okay. So what can we say in addition to this? Or rather, what can we say as a consequence of this full rank? full row rank. So recall that it is a convex optimization problem, so we want to sorry, we want to see if we can apply Slater's condition.
Yeah, Slater's, where there exists. Yeah, I think, yeah, that is the one.
So the consequence of this, A being full row rank, which means that can just find feasible point, feasible solution that satisfies Slater's condition.
Yeah. I think this is the one condition. I did not write that out in my solution notebook. That's why.
Yeah.
Get it.
So what can we say as a consequence of this?
Uh,
Strong
yeah,
duality.
strong duality. Yeah, strong duality.
Okay. So it is clear, right? So for example, I mean, just to expand on what I said here, let me write it. So why is this true? We can find feasible solution that satisfies Slater's condition. What does it mean?
Yeah, it just means that it's a full rank means it always have a solution, non-trivial solution.
Yeah, but we are saying Slater's condition. So what we really want to find? Each of the constraints is affine, right?
Yes.
Correct. So what do we do here? This is an affine constraint. So there is this corresponds to this affine constraint. This row corresponds to this affine constraint, and this here we are given that this A is full. Well, you can see here it's not given. You can just see that this full row rank. Right. So how do we see that? I mean, sorry. How so? What do we do about this condition you want to satisfy? So the null space has many solutions, right?
Yeah.
I
Just
mean,
pick one of
no,
them.
yeah. Just pick any of them. So
Yes.
let's say if there is an X that satisfies the solution, meaning Ax equals to B.
Yeah.
Then because null space is non-trivial, I can just
Yeah.
pick
You
X
add it
some.
to.
Yeah, I can just add to
Yeah.
it, right?
Yeah.
So what did I do? I ended up finding some X hat, which is giving me what? Equality, right? I mean, I
Yes.
just need
Yes.
to satisfy less than equals A. I don't need to satisfy
Yeah,
strictly equal,
yes. Any of them should fine. Should suffice. Equality should suffice. Yeah.
right? So X such that Ax equals to B and X plus X naught where Ax naught is 0 also has so X hat equals to A X Ax hat minus B equals to A X plus X X naught, I mean the null space vector, minus B is nothing but B plus 0 minus B, which is 0. Okay.
Yeah.
Right. So just one more question and then we are done.
Yeah. This was a long day.
Yeah. So here we have exponentially decaying function. That's our objective, such that our constraints are this. Okay, and so as usual we'll call this P, and optimal solution we'll call it P star. I mean optimal value, sorry. And D star is the optimal value of the dual. The question is, what is P star minus D star? Right.
So how to means I did not get this question. Means I don't know.
Yeah, I mean here you'll have to, because you can't say offhand is you can't really check the strong duality, right? It's not like you have a candidate point and you can check Slater's condition and then say, okay, strong duality holds, you just find P star and then that will be it. No, you can't do that. So you just have to go what do we say? You just have to proceed with the usual calculations.
Okay, fine.
Okay, so yeah, so what do we do in this case? Any thoughts? Okay, so let's say we ignore this. What will be the minimum value for this?
E to the power minus, that will be 0, right?
No, the value. So that 0 will be the x value.
Okay.
Okay, and the minimum value will be 1, right?
Yeah, minimum value will be 1. Yeah.
Okay, so we have some guess right now. Yes.
Yeah.
Okay. Let's see. So okay. I mean, for now we are just saying that okay, maybe P star is 1. Maybe. We'll come back to this. We'll just focus on the dual right now. There's only one constraint, and there are two variables. So what? So yeah, of course, lambda is greater than or equal to 0. So what will be the infimum of this? So the only problem that's going to come here, right? Because this could blow up and this will die down.
Yes.
But it's an exponential.
Exponential will always dampen the other effect, right?
So basically this is 0.
Yeah, this is 0.
Right. So D star is 0. So let's come back to P star. What's the constraint? E to the y greater than or equal to x squared, right?
Yeah.
Okay, so how will that look like? Okay, actually you can't really write that here. It will be, yeah, I don't think I can write that here. So
that means y and x are different, right?
Yeah, y and x are different, but can I say something just by looking at the problem here?
Yeah, we can definitely say something, yeah, because there will be a value which makes it exponential greater than the quadratic, right? Based on that, we can say something. For each value of x, y should be a certain.
Okay, let's focus on this constraint. So, what about this quantity? Does it attain 0 value at all?
No.
So, what is this saying basically?
Okay. It's only possible to be equal to 0.
Exactly. So yeah, exactly. So feasible region x has to be 0.
It's a singleton, right?
Yeah, I mean no, x has to be 0. Y can be anything.
Okay. X has to be 0. Yeah. X has to be 0.
Right? So x anyway, x is 0. That's the only possibility we have. So what's the minimum value here?
0 is 1.
So it's fine, right?
Okay. So there we have the answer.
Yeah. So p star minus t star will be.
Oh, it was just like going through the steps one by one. Yeah.
Yeah. So here you get a bit used to actually actually calculating these dual functions. So I don't know the kind of question that will be coming on me the next week, but if time permits, again I can maybe show a few more questions where this calculation can get complicated at times. So this is where there's, although the problem you end up convexifying the problem, but then it's difficult to sometimes compute these dual.
Yeah, because we need that, right, directly to compare the two values.
Yeah,
right?
so what I'm saying is you'll have to, a lot of times what you do is you end up breaking this objective into many cases, and then accordingly you will get a form for the dual, and of course then based on that dual you will want to maximize that dual, right? So maximizing that concave function, which will ultimately give you the convex problem.
So then you will have the duality gap for many different separate subcases, right? And then compare those.
No. I'm just saying that you will have to. The dual form will get complicated because you'll have to get that final expression by going through several different cases based on the objective that you have. Or duality gap has to be the same. It cannot be different for different cases. Duality gap will be p star minus t star.
Yeah. My bad. Yeah, it will be single duality.
Yeah, and again, just to maybe say a bit more on that. So why is d star such that, let's say there are two dual values. Why are they same? Not dual value, sorry, the dual optimum.
Yeah, because we are taking a infimum, right?
No,
sorry, max.
See that, okay, so two things. This is a dual function. It's not a dual problem. My dual problem is this. This is a concave function.
Okay.
And sorry. So point-wise sup or max of concave functions is convex, right? So
that's right. Yeah.
So again, going back to the that doesn't make sense. Let's see. So at any point, if you are at any point, so this is the maximum.
Yeah.
Right?
Yeah.
So this, by the way, what I did here is a hint perhaps to also prove this. So maybe just try proving this, and if you are having any difficulties, let me know.
I'll try that. Definitely. Yeah. So at the point where the maximum switches from one affine plane to another, that will be non-differentiable, right? Because there are many affine planes, as you have written, right? There is a crossover at various points.
So right now we are not worried about differentiability. We are just talking about. So we don't need the differentiability definition.
Yeah, I'm just commenting. That's all.
Yeah, I mean it has to depend on what should I say?
The problem formulation, perhaps, right?
It will have to define on how what the orientation of these
yes, and the specifics of the problem. Yeah.
Okay, is that fine? So
it's fine. It's fine.
Gone over the time limit.
Yes.
We will stop here. So let me. Are there any questions, or we can stop maybe?
No, it's fine for now. Yeah.
Okay, so let me stop the recording first.